Hi everyone, welcome to my third year annual review meeting. I would like to present my progress report regarding my PhD topic, the cost of roughness predicting the drag penalty of fault ship's hull. So this slide is as an introduction. On the left side, this is the ships before they replace the anti-fouling coating, and on the right side is the result. So this happened after 5 years dry dock period. So the goals to replace the anti-fouling coating and clean the ship's hull is to restore the ship's hull to a smooth surface, so the ships can reduce the drag and improve the fuel efficiency. And the next question is, when is the optimum time to clean the ship's hull? Are they need to wait until the ship's dirty like on the left side here? Because let's say the ship's dirty starting from the third year of sailing, so they need to wait. They need to pay extra fuel for the rest 2 years of sailing. So we can avoid this by let's say the ship's operator have a function that based on the measured topographical roughness, and then they can predict the ship's drag penalty. This will answer when the optimum time to clean the ship's hull. But the problem is we lack of this predictive correlation, especially scientifically approved. So to answer this problem, we have a research collaboration between Unimelp and Samudra Indonesia, the owner of the ship. So the research objectives first is to improve the predictive correlation of the KS, or equivalent sand grain roughness, for realistic ship's hull roughness. And second is to test and improve the full-scale predictive capability of laboratory experiments to answer it. So I just want to remind you that on the ships, Sinar Morotai, on 68 meter downstream of the ships, we installed the marine grade window as an access for laser Doppler anemometry, so we can measure the turbulent boundary layer of the operating ship's hull. And from this boundary layer measurement, we can calculate the delta U plus, so it will directly tell the drag penalty of the ship's hull. And the state of the hull roughness from the ships in every LDA measurement we recorded with the dive inspection, and we periodically monitor this until the next docking cycles, so for 5 years. Since dry dock in March 2022, so we have 5 years until the next dry dock in 2027. So thus far until April 2024, we measured 4 times, and on the left side this is the delta U plus, and on the right side it directly corresponds to the drag penalty of the ship's hull. So based on the dive inspection until April 2024, we saw that from the dive inspection there is no sign of biofouling, so that means the ship's hull remains clean. And from these LDA measurements, that means it shows that in average the delta U plus is around 4 with plus minus 1.2 as the error margin for the measurements, and we call this as the baseline drag penalty. So up to April 2024, we can see the picture comparisons here from the same place that the ships there is an anti-fouling paint degrade, so that means the red paint is the anti-fouling paint. So in the next following years, so the biofouling will growing on the ship's hull, and on October 2024 we also have an evidence that the biofouling starting to grow on the ship's hull. And this, if we continue measuring the boundary layer of the ship's hull, the delta U plus will increase, and also, as well as the drag penalty of the ship. So this is still the trajectory lines. The problem is if we compare between the biofouling growth effect compared to the baseline drag penalty, what's the meaning of this baseline drag penalty? So this corresponds to 25% drag penalty compared to the hydrodynamically smooth hull. So let's say this area here is really big compared to biofouling growth effect. So the shipping industry on Earth, so it consumes 400 million tons of fuel yearly, and so it's about 300 trillion Australian dollars per year. So let's say this baseline drag penalty happens on all of the ships around the world. So that means the amount of money wasted is within the range of billions of Australian dollars. So it's big effects. So the question next is what's causing this baseline drag penalty? So this is from the flat bottom area. So this is below the ship's hull, and at the flat bottom area we can see there are 3 major sources of roughness below here. First, start from the paint job roughness. It's all in everywhere. It's just from the paint job finish. And second is the weld seams. The weld seam is indicated with these yellow lines, and the last is docking blocks indicated by the green squares here. So what are the docking blocks here? So if we reverse back to the dry dock period, this is the ship's hull in the graving dock, and we can see that that's the weld seam is big. So and then if we compare to if we see down there, this is the photo on the right side under the ship's hull, and these are the docking blocks. So the docking blocks provide access to the bottom hull, so the cleaners can clean and repaint the ship's hull. The problem is this docking block leaves a pattern where the anti-fouling coating has not been applied. So on top of this docking block, there is no new anti-fouling coating, so that makes the biofouling growth faster in this area. So from these three major sources of roughness, we want to answer first, start from the paint job roughness, the contribution of this roughness to the total drag penalty. So we capture this with delta imprints at 5 representative spots, and we scan these imprints with Nanovia optical profiler, and we test from 5 roughness. We choose 2 based on the highest effective slope case and the lowest effective slope case, and we measure the drag in the lab to know the drag penalty contribution. So this is the size comparison of the imprint. So we need to expand this roughness to fill the entire wind tunnel area. So I need to scale up test lab and manufacture with the CNC machine, and at 3.8 meters downstream at the wind tunnel, I measure the drag with drag balance and hot wire measurements. And the conclusion is for the lowest effective slope case is contribute to 13%, while the highest effective slope case is contribute 16% drag penalty. So from this baseline drag penalty, we've just answered that the orange peel roughness contribute up to 16% drag penalty, and the remaining of difference between what we found on the field and the lab should be the combination of these 3 roughness: paint job, weld seam, and docking blocks. So to answer this, we need to know the case of these roughnesses. So besides the LDA measurements, we also do a dive inspection. So we send the divers to operate multiple camera, including the 3D scanner. So on this video, this is the diver scanned these surfaces, and from the 3D scan here, we can generate the roughness statistic from the surface scan from the ship's hull. So the output from this dive inspection is first is the ship's hull conditions, because from this video we can analyze and we can say that is the ship's hull clean or dirty, and also second is we can get the roughness distribution, because all of the footage that we have, we know the exact location from where it's come from. And the last is we have the 3D scan roughness topography, for this one as the example. So the next question is, how rough are they? So we can try to estimate how rough are they with the existing predictive correlations such as Furogi et al. 2017. But the problem is it accurate? Can we use this equation for ship's hull roughness? So to answer that, I reconstruct all of the 3 scan surfaces on the docking block because it's brought faster, and I compile the surfaces, these scanned surfaces, based on effective slope and skewness. So here's the effective slope versus skewness plot, and this is the orange peel area, and then I plot all of the scans here is on the plot here in a chronological order. So and also put the dry dock roughness as an example here, and most of the docking blocks area are lying on this red area. And on the blue one, this is not on the docking blocks, but what we got this from the sides, but it's still a biofouling roughness. So to answer how rough are these roughness, let's try this predictive correlation from Furogi. But the problem is this predictive correlation is built from this area. So we can use Furogi but it's not the parameter studied or training data to build this predictive correlation is not wide enough to answer the ship's hull roughness. So it's not enough. So that means we need a new predictive correlation, and I plot all of the existing parameter roughness study. And let's say if I build a new predictive correlation based on this roughness that humanity tried to study, the problem is still not enough, because the existing roughness study does not cover all of the roughness statistic from the ships, and most of them are not synthetic roughness. Most of them are synthetic roughness, so most of them are not real roughness. So I need to improve this predictive correlation to answer how accurate the predictive correlation. So at the end of my study, I need to add more training data on this area. but the problem is it's challenging because if every single point here requires extensive training data which involve a costly experiments or simulations. So from our surface database, so I choose select one to be tested in the wind tunnel. I choose this surface, and this is the video when the surface is taken. So on top of it, this is the Z or elevation profile, elevation map. So by adding roughness element on this surface, it will shift the effective slope and skewness parameters space on the left side over here. And when I keep going at more roughness elements here, it will stop at this point. So currently, what am I doing in the lab? I'm trying to measure the drag of this surface from the super rough surface covered with a lot of barnacles using drag balance and hot wire anemometry. So by reducing roughness element in this measurement, so let's say if I remove half population of the barnacles, it will expand the range of parametric roughness studied. So when I keep removing the roughness element and then I retest it and keep removing and test it, and so the outcome from this experiment method will be beneficial to improving the predictive correlations. So from this improved predictive correlation, so let's say now I will have more confidence using this to answer the how rough and the combination of the weld seams and docking blocks on this question. So this will indirectly answering. The first is to improve the predictive correlation of KS realistic roughness signal, and also the second research objective, this also will answer the it will directly try and test the full-scale predictive capability of the laboratory experiments. So regarding my fourth-year research plan, on the fourth-year agenda, because you know that I'm still doing the last case of laboratory experiment, I just need to finish this, and it's planned at the end of this month it should be finished. And then after that, I just need to synthesize all of the outcomes from these experiments into my thesis. And at the end of this year, I'm planning to submit my thesis. And about the thesis writing progress report, to be honest, that I don't have much enough progress because I'm still busy with the labs experiment. And after this, I will continue focus on writing. But from actually, there are three major experiments. First is field, and then recently clipped ship's hull, and this is ongoing experiments. For the field experiment, it will cover most of my thesis chapters, and for the clean ship's hull or the orange peel, it will cover chapter 4 and chapter 5, and for the ongoing experiments, it will involve in the chapter 5 to chapter 7, especially to improve the predictive correlations and to validate the ship's hull drag penalty in a full scale. So yeah, I need to complete this immediately. So that's the end of my presentation. Any questions? Thanks.